Tau is a representation, any irreducible representation of K.
And how do I reconcile the definition of the rough pattern?
Mu is the highest weight. Mu is any highest weight of tau, and there may be more than one highest weight. There may be more than one choice of delta plus with these properties, but the height doesn't depend on any of those things. And, well, I didn't say, of course, this maximal torus is unique up to conjugation by K, and the Borel is unique up to conjugation by K. All these things are their choices, but they don't matter. So now that I've got a height, I can define a lowest K type of this GK module to be any irreducible representation of K that minimizes this height and which occurs in the GK module. So that's exactly the definition that I used for SL2. Pick out the smallest integer occurring here. Well, and what's I'll say just what's clear is that if M is a non-zero GK module, then the set of lowest K types of M is non-empty and finite. Sorry. Well, in the reductive case, you could do something stupid, but if it's irreducible, anyway, that's true. Okay, so I want to, in the case of SL2, I used a lowest K type to construct a cohomology class. I want to try to do something similar here. So, well, if I had this real cartan, it would be the fixed points of theta, the compact part, and I forgot a parenthesis, this exponential of the -1 eigenspace of theta. So I'm still talking about an irreducible GK module. Sorry, I should have called this tau not a lowest K type. Actually, let me make notes of the typos so that I actually fix them later. So tau naught is the lowest K type, and mu naught is the highest weight of the lowest K type, and then I picked this Borel, well, this Borel making mu 0 plus 2 rho c anti-dominant. Okay, so here's the theorem about constructing cohomology. In the case of SL2, the case when mu was at least 2 was easier. Same thing here. This condition mu 0 plus 2 rho c minus rho is regular and anti-dominant. that's the same condition as mu being an absolute value of mu being at least 2 in SL2. Okay, so anyway, let me assume that. Then the statement is this should be in the cohomology. It should be the cohomology of this NF with coefficients in M, and I'm interested in this weight U naught plus 2 rho C. So this M was missing on the slide. And in that unique degree where it's allowed to occur, the number of times that weight occurs is the number of times that the representation tau appears in M. So what that's telling me, well, yeah, so I never introduced the notation. So if M is an algebraic representation of a reductive K, I'm certainly going to need this. I want to define M tau is the space Hom over K of the space of tau into M, and this is called the multiplicity space. And then M is naturally isomorphic to a sum over tau and e tau irreducible of K of M tau tensored over C with e tau. So I never wrote this. I'm going to need it a lot. So eventually I'll make some slide that has these statements. But M tau means a multiplicity space, and so that's the story. So since I chose tau naught, tau naught was supposed to occur in M. So if I put tau naught here, this space is non-zero, and so it's a finite dimensional space. It has a weight for the action of this split part. So just write nu F for some weight, some eigenspace for these AF guys acting on this space. Okay. Well, that's the end of the theorem. And now I can define the Langland's parameter that I want to attach to M. I want to use this fundamental cartan. For the lambda, I want to use this mu plus 2 rho C minus rho. Well, remember, lambda bar is supposed to be in some quotient of the characters. I'll flip back to the previous slide. Yeah, these characters, the mu is a character of the fixed points of theta. It's in this quotient. So it's in the right place. So that's the lambda bar. And for the nu bar, the weight of A, I use just some choice of a weight that appears there. Okay, so that's how you attach a Langland's parameter to M, and you see that it's set up so that this, this T upper theta module, well, this mu plus 2 rho c minus rho nu f, this appears in HS of this, sorry. That's what the Langland's parameter has to do with Lie algebra homology, and as a consequence, so this statement in the box is true by construction, and we're going to learn everything about cohomological induction from Peter, probably. There's out of this parameter gamma, you can make a cohomologically induced module. There's some notation. And because you can study properties of this cohomologically induced thing, actually I had a bunch of things written here, but I ran out of space on the slide. Anyway, one thing which is true is that this representation we're looking at sits in an algebraic family of representations. So this is one of the big ideas for the Atlas project. Representations come with discrete parameters, which are related to representations of K, and so they just are what they are. And they come with continuous parameters, which are painful. And so the idea is you understand these representations by deforming the continuous parameters from places that are hard to understand to places that are easy to understand. So that's the picture. So what's this tell you? So I said that if you had an irreducible GK module, well, I in various cases explained how to define a Langland's parameter. I haven't finished saying how to do that in general, but eventually we'll always be able to define, we'll attach some theta stable H and these things. So here are the big ideas. First, the infinitesimal character of M is given by the parameter in this really simple way. So this is one of the built-in, I guess it's a built-in function in Atlas, which I actually could have written, I think, practically, sort of, kind of, that computes the infinitesimal character from the parameter. That's what it's doing. The lowest K-types of the representation are very closely related to this discrete part of the parameter, this lambda bar. The third thing, which I haven't explained at all, but which was Langland's original idea, is that the way the matrix coefficients, well, I wrote M, but really I should say the corresponding representation of G of R, that representation of G of R has matrix coefficients, and the group is infinite. You can look at how fast the matrix coefficients go to infinity. And what Langland's did was he looked very carefully at how matrix coefficients went to infinity, and that's how he extracted this nu bar. That's what nu bar is telling you. Okay, and that's as far as I got on the slides. So, yes?
This description was Yeah.
Well, so here, what's the bar mean? So, so in this general Langlands parameter setting, we have this T is H upper theta. This lambda bar is supposed to be a character of T. Well, there's some row shift. And what happened is that the characters of T, I mean, this is an algebraic character of T. An algebraic character of T is, and these are the algebraic characters of H, that every character here is the restriction of a character of H modulo the characters that are trivial on T. And so that's this quotient, x upper star of H divided by 1 minus theta, x upper star of H. So so this lambda bar is something in here, and lambda is a representative in x upper star of H. And well, that really there was a plus rho. And so instead of being a nice vec, it has to be a rat vec because of the plus rho. So what I'm going to do for the next 10 or 15 minutes is say a little bit about well, I was about to say I'll give some more details about how the Langlands classification works. I think maybe that's a mistake. I think what I'm going to do for the next 15 minutes is what I was supposed to do for the whole lecture today, just to start talking about Hermitian forms. But are there questions about what I've done so far?
So what I'd like to ask before is that the construction that you described, in some sense, gives us some concrete representative for lambda.
The construction gave a concrete character of this group. So we are talking about a particular character of this group, but to write down such a character in terms of the root datum, you write it as a choice of lambda that restricts to it. Other questions? Okay, so let me so somewhere I have some slides about Hermitian forms, and so I think I'll be able to put slides for this material in these just later today. We'll see what happens. So here's the topic. It's Hermitian forms on GK modules. So repeat that if tau, E tau is an irreducible of K, well, M is going to be my GK module. I define M tau is Hom over K of E tau into M, and then M is isomorphic to the sum over tau and E tau modulo equivalence of M tau tensored over C with E tau. The way this works is that if you have something in one of these spaces, an element of E tau and a map from E tau to M, you map it to phi of E. That's the way it works. So you may think that all I'm doing is writing M is the sum over tau of this is something that people write a lot. That they say that you can write a representation as just a sum of irreducibles with multiplicities. This is a much weaker statement. I don't like this. This isomorphism that's written here is entirely natural. So what? For example, suppose that M carries an invariant Hermitian form. I haven't explained this. I need to explain exactly what that is, and I will. And I also want to suppose that E tau carries an invariant Hermitian form. And this, for us, is essentially always going to be automatic. The reason that it's automatic is that K of R representations are unitary. And anyway, this form on E tau, I'll write like that. Then what happens is this Hom over K of E tau into M it inherits a form which I could I don't want to try to explain that properly, but but it's true. And what happens is that this decomposition over here is now an orthogonal decomposition on the level of forms. So the if I compute the pairing between two of these guys, this is going to be the pairing between phi and phi prime in this form here.
Dave, you should stick to darker colors.
Okay, sorry. Multiplied by the pairing between E and E prime in E tau. So there'll be natural forms on these pieces, therefore a natural form on the tensor product, and the mapping, this is all natural. And so, well, I still have to make these statements more precise, but so this kind of crude formula, M is the sum over tau, M tau, E tau. This is now, actually I'm going to write it differently, sorry. I'm going to write it M sub M of tau, E tau. So this M sub M is a function from k hat to the integers, and it's this multiplicity function. This describes the restriction to k. Now, what happens? Well, I mean, this M sub M of tau is the dimension of this nice space M tau. That's good. And given Hermitian form, on M and all these E taus, and these guys, you might as well take to be all positive, since, again, all representations of K of R are unitary. You get, well, if this is non-degenerate, you get a non-degenerate Hermitian form on each multiplicity space. This M of tau dimensional space. So This is the form that wow. And so this form has a signature. P of tau, Q of tau. Well, so what happens is I get these two functions. I should call it PM and QM. PM and QM that go from K hat to the natural numbers. And as I say, PM plus QM is equal to M sub m, this multiplicity function. And this form on M is positive definite if and only if, well, UM is 0. That's the story. So this formalism of multiplicity spaces lets you write down, if you ask about computing a Hermitian form, you're sort of asking about computing a bunch of Hermitian matrices and asking about their signatures, and that sounds like moderately painful linear algebra calculations. But all we care about, well, we have this big subgroup K, which is more or less acting unitarily. And that, we can sort of divide by that. And so we end up with these much simpler functions which carry all the information about whether a representation is unitary. So I haven't actually defined much of anything, but this is